Through the years, the need to manage water for various uses has given engineers the opportunity to study many different aspects of this fascinating liquid. Although water has been controlled to a great extent, it still challenges engineers with many problems. Water flowing from a reservoir changes from a tranquil state to one where there is a lot of energy produced. This change provides us with one of our most important benefits of water, hydropower. But fast-moving water creates problems too. One of these problems is cavitation. Conditions for cavitation occur when water is traveling at high velocity. When cavitation develops, it can produce devastating damage, requiring extensive repair. As we learn more about cavitation through field studies, mathematical and computer modeling, laboratory studies, and careful construction practices, we can reduce or control the causes of cavitation and, subsequently, the damage it can produce. Damage caused by cavitation in large hydraulic structures is not a newly discovered condition. One of Hoover Dam's tunnel spillways was severely damaged in 1941. Many structures over the years have suffered damage by cavitation. In 1983, a combination of factors served to produce some of the most spectacular and devastating cavitation damage ever experienced by the Bureau of Reclamation at Glen Canyon Dam. The 1983 water year in the Colorado River Basin began quite normally. The first 3 months of the year recorded precipitation at or slightly below a typical year. The snowpack forecast for the year was, at that time, about normal. During April and May, however, unusual heavy, wet snows blanketed the mountains of the basin, and runoff forecasts began to rise. By June, snowpack was 131% of normal, and still growing. Then, hot weather seemed to hit everywhere at once. The rivers filled. Snowmelt runoff for 1983 eventually reached 210% of normal. Nearly every tributary to the Colorado River overflowed its banks, and Lake Powell reached new heights. In an effort to control the rise of Lake Powell, in mid-May the dam's power plant was operated at full output of 800 cubic meters per second. As the inflow to the lake continued to grow, the capacity of the power plant to pass it became insufficient. On June 2nd, the left spillway at Glen Canyon was opened to pass the surplus flow. Water roared down the spillway at 160 kilometers per hour. Engineers estimated that cavitation damage would probably occur if the spillways were used for long periods at high velocities. On June 6th, the left spillway was closed, so an examination could be made. Holes in the tunnel lining, caused by cavitation, measured up to 6 meters wide by 1 meter deep. It was decided to operate the spillways at minimum flows in an attempt to reduce the damage. To reduce spillway use, flashboards were added to the top of the spillway gates. The first flashboards were made of plywood and stood 1.2 meters high. The outlet tubes were opened to bypass an additional 480 cubic meters per second of water. Now, about 1,500 cubic meters per second were thundering through the spillways and the outlet tubes, and the lake was still rising. On June 19th, the left spillway stopped sweeping. This indicated that the cavitation-caused holes had deepened, resulting in erratic flow patterns. The flow in the left spillway was raised from 340 to 480 cubic meters per second, and the sweep was reestablished. In late June, water released from the dam peaked at 2,600 cubic meters per second, and inflows were at 3,300 cubic meters per second. The spillway could not be shut down because the plywood flashboards on the gate were not high enough. Steel flashboards, 2.4 meters high, were then installed on the gates. In early July, the dam operators were able to reduce the spillway flows to safer levels. With the lake 2.5 meters into the surcharge pool, the gates were lowered, and an inspection team descended into the spillway tunnels. After descending part way into the tunnel, the damage became so rough that the team could proceed no further. In September, the spillway tunnels were completely dewatered, and extensive damage was revealed. Tunnel floor sections were covered with rubble torn from the elbow sections by the pounding water. The Glen Canyon events of 1983 had proved to be one of the most dramatic and serious cavitation-induced episodes ever recorded. Although the system of dams and reservoirs on the Colorado helped to keep downstream flooding damage to a minimum, the problem of cavitation was very dramatically emphasized. The research effort to study and attempt to control cavitation was intensified in the Bureau of Reclamation. Just what is this destructive force called cavitation? Dr. Henry Falvey, a technical specialist at the Bureau of Reclamation's Engineering and Research Center laboratory in Denver, explains.
The damage produced here at Glen Canyon Dam is the result of a condition which exists when a hole or a cavity forms within a liquid. There are several ways in which holes or cavities can be produced within a fluid. For example, when you pour a carbonated drink into a glass, bubbles form and rise up through the liquid to the surface. This formation of voids or bubbles is called gaseous cavitation. Another type of cavitation is vaporous cavitation. It is this type of cavitation that we are concerned with in hydraulic structures. Boiling water is an example of vaporous cavitation. At sea level, as water is heated, a temperature is reached when small bubbles can be seen to form at the bottom of the pot and rise through the liquid to the surface. These are bubbles of water vapor, not air. At higher altitudes, water boils or vaporizes. We can say it cavitates at much lower temperatures. At some altitude, the pressure is so low that the water begins boiling or cavitating at room temperature. In hydraulic structures, the water pressure may become low enough that the water will cavitate or vaporize at the temperature of the water within the reservoir.
There can be many different types of surface irregularities that create conditions for cavitation. An offset into the flow, an offset away from the flow, an abrupt slope away from the flow, a void or transverse groove, and a rough surface are some of these irregularities. Small surface imperfections, a groove, a piece of wood debris left during concrete placement, sloppy finishing, all can become the beginning of very serious damage to a hydraulic structure. A fraction of an inch break in alignment where a small lip has been left in a section of concrete can cause cavitation. The damage at Glen Canyon began with just half-inch irregularities. Concrete used to construct tunnels and spillways has an inherent characteristic that can cause cavitation. Calcium carbonate deposits can grow as water, seeping through cracks, leaches the lime from the concrete. The process is similar to the formation of stalactites and stalagmites in limestone caverns. Damage caused by cavitation is mainly the result of a mechanical process. There can be several different ways a bubble collapses and causes cavitation damage. When a spherical bubble collapses, it rebounds and generates tremendous pressure waves in the surrounding water. A boundary, such as a tunnel wall, causes a non-symmetrical collapse of a bubble. The jet from the collapsing bubble and the rebound pressures can damage the most durable materials. A bubble collapsing in a swarm of bubbles sets up a chain reaction, creating large pressure intensities and a great deal of noise. This damage-producing cavitation takes place in a very narrow region close to the tunnel wall. Cavitation damage is progressive. In metals, one bubble deforms the surface. A second causes a fracture zone, popping material away. Cavitation can be caused by the formation of calcite deposits, taking several years to develop. Once cavitation begins, a leapfrog effect occurs. The damage continues downstream because each succeeding hole causes more cavitation. This damage may develop in only several days or weeks. As more damage occurs, the lining becomes penetrated at some point. This causes differential pressures across the lining, breaking off large pieces of concrete. Finally, the foundation material begins to erode. Huge chunks of debris are swept loose and large holes produced. The extent of the foundation damage is dependent upon the strength of the foundation material and upon any joints or failure planes in the underlying material. At Glen Canyon, the high velocity of the falling water, remember it was 160 kilometers per hour, produced holes in the surface by cavitation. At this point, damage caused by cavitation became insignificant relative to that caused by erosion from the high-velocity jet. Mechanical failure was in evidence. Reinforcing bars were physically torn from the concrete. Some of these still had pieces of concrete attached which flailed and pounded on the liner. Some of the debris left in the tunnel at Glen Canyon Dam during the summer of 1983 was as large as a small cabin and had to be dynamited into smaller pieces before it could be removed. When cavitation occurred at Glen Canyon Dam, it ultimately led to a hole approximately 35 meters long, 10 meters deep, and 15 meters wide. Although the spectacularly large hole at Glen Canyon was not caused by cavitation directly, the entire process was initiated by cavitation damage upstream in the tunnel. Thus, if we can eliminate the initial cavitation damage, we can also eliminate the formation of extensive damage. The formation of cavitation in the field can be investigated in the laboratory. The essential requirement to conduct the laboratory study is to know how to scale model results to field values. The scaling law for cavitation is known as the cavitation index. A site-specific model is used to determine the cavitation index of the surface irregularities. Hank Falvey explains.
We measure the pressure at a point on the wall and the average velocity near that point. These can be expressed in a mathematical relationship. The pressure at the wall minus vapor pressure, which is approximately equal to minus 10 meters, divided by the velocity head. This gives us an expression called sigma, or the cavitation index. In this model of a tunnel spillway, we measure the pressures by small piezometer holes drilled in the wall of the spillway. The water velocity is either measured or calculated knowing the flow depth and discharge. From these quantities, the cavitation index can be calculated. It is important to note that since cavitation occurs within the flow for surface irregularities, the pressure at the wall can be positive and cavitation will still occur. To determine if cavitation will occur, we need to determine the cavitation index of the structure and compare it with the cavitation index of surface irregularities. The irregularities, or roughness elements, include chamfers, grooves, and holes. These can be tested in a water tunnel or low ambient pressure chamber.
The low ambient pressure chamber at the Engineering and Research Center lab is the only one of its kind operating in the United States today. Tests can be conducted with either closed conduit flow or with a free water surface. The pressure can be lowered to about 1/10 of an atmosphere. Therefore, the water velocity can be quite low and still create cavitation. By studying the formation of cavitation for various roughness elements, mathematical charts can be developed that show when cavitation will occur. Using the chamber to test roughness elements will enable development of spillways and energy dissipators that are cavitation-free or designed to keep cavitation damage to a minimum. Testing can also help the engineers determine the difference between cavitation damage and erosion damage. Recognizing this difference is extremely important because a cure for cavitation damage is not necessarily a cure for erosion damage. The conditions that create cavitation are unique to each situation. Therefore, the solution to prevent or reduce cavitation damage in a hydraulic structure will be unique to each particular structure. Perhaps one method of prevention or correction may work. Perhaps a combination of measures may be required. Testing reveals what methods should be attempted and where they should be applied. Stronger construction materials might be an answer. This test facility in the laboratory was used to compare a variety of materials and the effect cavitation had on them. The testing indicated that a given amount of cavitation would occur in 3 hours to concrete. The same amount of damage occurred in polymer concrete after 15 hours. In aluminum and copper, after 200 hours. In carbon steel, after 1,000 hours. And in stainless steel, after 6,000 hours. Tighter construction specifications and practices may help reduce damage caused by cavitation. Specifications should require that surface irregularities be ground down or removed and a smooth finish achieved. In some structures, aerating the water flow is having a high degree of success. In effect, the introduction of air into the stream reduces the sonic velocity in the water dramatically. Reducing the sonic velocity, in turn, reduces the pressures generated by the collapsing cavity. The sonic velocity varies with air content. With 6% air, this velocity is less than sonic velocity in air alone. A simplistic demonstration of this effect is shown with the water hammer equation, where delta V is the change in velocity of the collapsing cavity. G is the acceleration of gravity. C is the sonic velocity of the fluid surrounding the cavity. And delta H is the pressure rise due to the collapsing cavity. Reducing the sonic velocity by introducing air reduces the pressure rise. Air is introduced into the flow via an air slot. The design of the air slot uses a ramp to separate the flow of water from its boundary. This is done by installing a groove downstream of the ramp to allow entry of the air. The ramp is placed upstream of a point in the tunnel where cavitation will occur. Cavitation is a serious problem, producing extensive damage in hydraulic structures and creating potentially dangerous operating situations. Through the use of tests and models, Bureau of Reclamation engineers are developing materials and innovative techniques to deal with the problems of cavitation. The success of their work is being used in the field to greatly reduce or control potential cavitation damage.